question 1 wants us to draw a cell that we could use to measure the standard electrode potential for this, the Mn2 plus Mn1. Make sure you know what the half reaction is. I mean, if they haven't written it out for you. I mean, this one is very easy because it's just aqueous Mn2 plus 2 electrons going to manganese. So those are the only things you need in the cell. If you get asked one of these more complicated ones, you know, like this one for example, that would also need H plus in the cell. So write out the half equation so you know what needs to be there. Okay, so the key thing to remember is the definition of the standard electrode potential, which is the voltage in a cell when you couple the half cell you're interested in to a standard hydrogen half cell under standard conditions. Now, standard hydrogen half cell means that you're using this as your reference half reaction. Okay, so H plus being reduced to hydrogen gas. So you need to remember that that's the reference, the 0 volts reference point, and so you're going to measure the cell potential here, and that will tell you the potential of this one. So that means that your reference electrode needs to have a hydrogen electrode, which, remember, contains this kind of strange device where the electrode is contained within this hood, and the electrode itself is made out of platinum, because this half reaction doesn't involve any metals, so you can't make the electrode out of either H plus or H2, but you can make it out of platinum. And the hydrogen gas comes in as a stream through this side arm here, and then the whole thing is dipped in a pot which contains aqueous H plus. You should put the state symbols in, especially for the solution. It needs to be clear that this is a solution here, so draw the surface in and put the aqueous H plus there. Okay, so that's that side of things, and then we need the 2 connections to the other side. A wire with a voltmeter going down to the other electrode, and then also the salt bridge, which allows, remember, ions to pass between the cell, and that one has to be labelled salt bridge because there is no standard symbol for that, so you need to tell people that that's what it is. And then that's going to dip into the other pot with, again, a layer of liquid in it, like that. So this one is your manganese Mn2 plus 1. So this time we have got a chunk of metal. Manganese is a solid metal, so we make this electrode out of that, and the aqueous Mn2 plus ions go into solution. So that's the whole setup, but because it said standard electrode potential, we have to define the standard conditions. So that means 1 mole per dm cubed for the species in solution. I think you should specify 1 mole per dm cubed of what? I mean, strictly speaking, you know, it could be 1 mole per dm cubed of hydrogen, for example, which it isn't. So for the solution things, so H plus and Mn2 plus. Okay, so 1 mole per dm cubed for all of the reactants involved in the half equations that are in solution. 1 atmosphere pressure for any gases involved, which is the hydrogen, and everything at 25 degrees C. And you need to specify that as well, because it says standard electrode potential. Part B asks us to identify the strongest reducing agent out of all of the substances in the list that we were given. So the key thing to remember is that the reducing agent is the thing that gets oxidized in a reaction. So don't get confused by that, and when you stop and think about it, that makes sense, because a reducing agent's job is to reduce something else. So oxygen, for example, can be an oxidizing agent because it oxidizes metals or carbon or whatever it is it reacts with. So a reducing agent reduces other things, but of course in order to do that, it itself must get oxidized. And therefore the strongest reducing agent is the one which has the most favourable oxidation. Okay, the thing with the most favourable oxidation. And you need to sort of explain this in your reasoning. This part at least, I mean, you don't really need to say that, but you need to say this, that the strongest reducing agent is the thing with the most favourable oxidation. And that, of course, means that it has the most negative standard electrode potential. Okay, because you've hopefully got the link. Reduction goes with positive, oxidation goes with negative, so the most negative electrode potential corresponds to the most favourable oxidation, and you can see that that corresponds to that one. Okay, out of all of those numbers, that's the most negative. So that points you towards that half reaction, but that doesn't answer the question, because that's not an oxidizing agent, that's shorthand for a half reaction, and you've therefore got to decide which of those substances is actually the strongest reducing agent. So that becomes clearer if, again, you write out the half equation. So you have Mn2 plus 2 electrons going to Mn, and you can see that the forward reaction there is reduction, because Mn2 plus is gaining electrons. So Mn2 plus isn't a reducing agent because it itself gets reduced. The reducing agent is manganese, because that's the thing that gets oxidized. When it goes in that direction, it loses 2 electrons. So the answer is that one, because it's the one that gets oxidized. So Mn is the strongest reducing agent. It's very common for people to work it out right, but just to leave the answer at that point, and you're always going to lose marks for that. So you've got to make it clear which of those substances is actually the reducing agent. Right, so part C invites us to construct half equations for these two half reactions and then to combine them to make the overall equation. So let's first of all just construct the half equations, and then we'll worry about what direction they're going in a minute, because we can write them as reversible reactions first off. So if we start with the H3PO2, H3PO3, so these are our two substances, and you can see this isn't just going to be a simple matter of adding electrons, because there's a mismatch in the oxygen. So you know you're going to have a more complicated half equation, and you need to memorize this recipe. So I've written it out there, and this needs to be there in your brain, ready to deploy as soon as you have this situation. So step 1, balance the elements other than hydrogen and oxygen. Well, that's phosphorus, and you can see it's already balanced, so no problem there. But the oxygen isn't. We've got 3 on the left, but only 2 on the right, so we need another one, and we balance it by adding a water in. Okay, because it's in aqueous solution, so that makes sense. That can act as a reservoir to provide extra waters. So now the oxygen's balanced, 3 on each side, but the hydrogens don't balance, because we've got 5 on the right, but 3 on the left. So that's step 3. Balance the hydrogens using H+. So you can see we need 2 more on this side, so we can put 2H+ in there. And now all the atoms balance, but the charges don't, because you can see it has 2+ altogether on the left, but nothing on the right. And that's step 4 then, is that we need to balance those up, and we do that by putting in the electrons, because that's how half equations work. So you can see this side is the one that's 2 positive. So that's the side that needs the electrons, and specifically it's more positive by 2, so we therefore need 2 electrons to balance that out. Once you've done that, just have a quick squint at it, check you haven't messed up. It's very easy to go wrong. So you just look at it and say, well, do the charges actually balance? And yes, they do, because you've got overall 0 on the left, 0 on the right. Always do those checks so you don't just sort of make mistakes and then keep them going for ages and have to go back. So now we can do the same for this one. VO2 plus going to vanadium 3 plus. So again, follow the steps. The vanadium already balances, so that's step 1. The oxygen though doesn't. We need another one on this side, so we can put that in. The hydrogens now don't, because we've got 2 on the right, none on the left. So again, we need 2H plus there. And the charges, well, at the moment we've got 2 plus and another 2 plus, so 4 plus altogether on the left, but only 3 plus on the right. So again, it's 2 positive on the left, but this time only by 1 electron. So we just put that in there. So now add them up again. 2 plus and 2 plus is 4 plus, and 1 minus is 3 plus, which balances the 3 plus. So those are now our correct half equations. So in order to combine them, they can't both be that way around, because at the moment you can see they're both going in the direction of reduction. So we have to decide which one should actually be going in the oxidation direction and write it the other way around. And we do that by looking at the electrode potentials. So this one is minus 0.5, this one is plus 0.34. So the vanadium one is clearly the more positive one. Okay, and what you have to remember is that positive goes with reduction. So because the vanadium one is going to go in, because it's more positive, it's going to go in the reduction direction, and the less positive one will go in the oxidation direction. So reduction is gaining electrons, so the vanadium one is already written in the reduction direction, because VO2 plus is gaining an electron to go that way. So that's fine as it is. But this one is going the wrong way. It should go in the oxidation direction, which means H3PO2 loses 2 electrons. So at the moment it's going right to left, so we've got to rewrite that one the other way around. So we just do that and say, right, we've got H3PO2 plus H2O now going this way to give you 2H plus H3PO3 plus 2 electrons. Okay, so these are now our 2 half equations, but we still can't combine them because the electrons are not going to cancel. We've got 2 in this one, but only 1 in that one. So when we add them up, there'll be some cancelling, but we need to have complete cancelling, and that means that we've got to double this equation, because then it will have 2 electrons on the left to cancel out the 2 on the right here. So we double everything in that equation, which means that becomes 4H plus 2 VO2 plus 2 electrons gives you 2 V3 plus and 2 waters. So it's all still balanced because we doubled everything, but now when we add them up, the electrons will cancel. This one, we could, if we like, replace that sign because we now know it's going to go in that direction. And then we can add them up. And you do literally that. So everything on the left hand side gets lumped together to make our overall left hand side. So we've got 4H plus 2 VO2 plus H3PO2 plus water. Okay, so all of those things, I haven't put the electrons down because we know that those are going to cancel out, but everything else is there. And then the same on the right, 2 V3 plus 2 waters plus 2H plus H3PO3. Before we leave it and say, right, great job done, we've got to look to check whether there's any cancelling to be done. Quite commonly we'll have ended up in the process of combining those with the same stuff on both sides, and you can see that is the case here, because we've got H pluses on both sides and we've also got water on both sides, and we cannot leave it like that. So we've got to do a bit of cancelling. So if we look at the H pluses, we've got 4 going down to 2. So if we take away 2H plus from each side, that term will disappear completely. Okay, so we've just got that, and this will go down to 2H plus. Okay, so we can do that. And then with the waters, we've got 1 here, but 2 on the right. So again, if we take away 1 H2O, this one will disappear completely, and we'll go down to 1 H2O on that side. And that should now be our complete equation. So that's the answer to the question. Final check before you move on. Ideally you check that everything balances. If you haven't got time for that, check that the charges balance, because that will usually pick up mistakes. So we've got 2 2s are 4 plus 2 is 6 plus on the left, 2 3s 6 plus on the right. So that looks fine, and that's our combined equation. The next thing it asks for is the cell potential. The cell potential, remember, is the difference between the two electrode potentials. You've got to make sure you've understood those differences. So these numbers that we've been given are the individual electrode potentials relative to that H2, H plus reference point. But the cell potential for this cell will be the difference between these two. So between minus 0.5 and plus 0.34. The point about the cell potential is it just has a magnitude. It doesn't have a sign. So it's not going to be either positive or negative. It'll just be a number. And we can just do it by subtraction. So we get that the cell potential is the difference between the two electrode potentials. So it's plus 0.34. And we've got to be very careful with the signs, because it's plus 0.34 minus 0.50 volts. Okay, so we're subtracting a negative number, which is the same, of course, as adding a positive number. So that's plus 0.34 plus 0.5 volts, which is 0.84 volts is the answer. If you'd subtracted it the other way around, you'd have ended up with minus 0.84, but as I say, it doesn't have a sign, so you'd still get the answer, 0.84 volts. Don't forget to put the unit in. Every time you calculate anything, stop and check, should it have a unit. The next thing is it asks us what difference it would make if we increased the concentration of H3PO3. What difference is that going to make to this cell potential? So we have to do that in steps. First, we have to find out what difference it makes to the electrode potential, which is what difference it makes to that number, and then we have to think what difference will that make to the subtraction. Okay, so the first thing is to realize that we've been thinking of this as an equilibrium, and so we can use Le Chatelier to give us the answer as to which way the half reaction will go. So if we increase the concentration of that, Le Chatelier says that that half reaction will shift to the right to oppose the change. Okay, so focus on the half reaction first. Don't look at the overall reaction. Now the problem is when you come to write it down, you're going to be wanting to talk about the equilibrium shifting to the right or whatever, and it needs to be very clear which equilibrium you're talking about. And the easiest way to do that, although it's slightly annoying, is just to write it out again. So just say, right, if we're going to answer this question, we're going to start by saying, right, this is the half reaction we're talking about. Sorry, we had a plus water there, didn't we, which has got rubbed off somewhere along the way. So that's the half reaction that we're talking about, and so by just rewriting it there, it means that when we come now to talk about which way it's going to shift, it's unambiguous what we're talking about. You get into big problems when you start saying the equilibrium shifts to the right or whatever, and they say what equilibrium you're talking about. So just, it doesn't take long, write it down again. And then you say, right, if we increase this, how will it oppose the change? So we say that this shifts to the right to oppose the increase in the H3PO3 concentration. So that's the starting point. Now the question is, what does that mean in redox terms? And you can see the shift to the right is reduction. Okay, the forward reaction going to the right is gaining electrons, so that's reduction. So we can translate that then into redox terms and say, i.e., shift in the reduction direction. Okay, so that needs to be stated, and then we think, well, what does that mean in terms of potential? And we know that reduction goes to positive. So if reduction is now more favourable, we're going more in the reduction direction, that means the electrode potential has become more positive. Okay, so E has become more positive. For this electrode. So that's not the same as the cell potential, that's the electrode potential. Okay, so make sure you've understood that we just used Le Chatelier to apply it to the half cell equilibrium, not to the overall reaction. Focus on the half cell and say, right, well, that will shift to the right to oppose the increase in that. And then explain, well, going to the right is reduction, so we've shifted in the reduction direction. And if reductions become more favourable, that equates to the electrode potential becoming more positive. So then we have to look at the difference, because remember, we got the cell potential by this subtraction, and what we're saying now is that this minus 0.5 volts is getting more positive. And of course, if it gets more positive, it gets closer to this one. Okay, so if it gets more positive, it might, for example, go to minus 0.4, and that's closer to this one, so the difference between them is less, and therefore the cell potential decreases. Okay, so you've got to distinguish between the electrode potential, which gets more positive, and the cell potential decreases. Okay, you can see that in a little diagram if that helps you to get your head around that this was if the E0 value was more positive for VO2 plus V3 plus than it was for H3PO3, H3PO2. And what we're now saying is, well, this one hasn't changed because we haven't changed anything to do with that one, so that one's still on the same level. But this one's got more positive, which means that it went up there, so I just exaggerated that. But you can see by getting more positive it gets closer, so the cell potential, which is that gap, has got smaller. So that's the answer. Okay, so make sure you spell it out in enough detail and think it through, and you'll be fine. Part D wants to know if a reaction is feasible when these two ions are mixed in solution. So the first thing we need to do is to identify and write out the relevant half equations. It doesn't actually tell you to write out the half equations, and in principle you could do the question without it, but it makes it much easier. So always, if you are given them in this shorthand form, and you may well not be, quite often they just write the equations out for you anyway, which makes it much easier, but if you are given them in this shorthand form, write out the half equations so that you can see clearly which direction is reduction and which is oxidation. So let's just quickly do that for these ones. So for the cadmium one, it's very easy because it's just cadmium 2 plus obviously has to gain 2 electrons in order to give you cadmium metal. And the vanadium one you have to work on, but fortunately we've done that one earlier, so we get VO2 plus 2H plus E minus going to V3 plus water, and we worked that one out in the earlier part. So we've got those two half equations. So looking at that, we can now see clearly what needs to happen if they're going to react, which is that if cadmium 2 plus is going to react, it needs to be reduced. Okay, it needs to gain electrons in order to form cadmium. So we can write that down. So for a reaction to happen, CD2 plus needs to be reduced. Okay, because the only way it can react is by gaining electrons. And V3 plus, well, when V3 plus reacts, it goes that way and it loses an electron, so V3 plus needs to be oxidized. So that's very obvious because the half equations are written down. I think if you didn't go through this step, you may well get those confused or something. So do that, and then we can just say, right, well, is that feasible? So we look at the electrode potentials, and you can see it's minus 0.4 volts for that one, and for the vanadium one it's plus 0.34 volts. So there's a very clear difference there, which is that the cadmium one is less positive. So we've got that the electrode potential is less positive for CD2 plus CD, and that means that the favoured direction for that one is oxidation. Remember, negative goes with oxidation, positive goes with reduction. So we'll write that down. Okay, so E0 is less positive for CD2 plus CD, which means that oxidation is the feasible direction. We could equally have focused on this one and said this has the more positive one, therefore reduction is the feasible direction. Doesn't matter which one you do, because you're going to come to the same conclusion. And the important thing is you then compare that with what we need to happen. And of course, as we said, CD2 plus can only react if it is reduced, because the only thing it can do is gain 2 electrons to make CD. So this is no good. It can only go in the oxidation direction. We want it to go in the reduction direction, so it's not possible. So we say, therefore, reduction of CD2 plus is not feasible. So really spell it out. And if that part of the reaction is not feasible, then the whole reaction is not feasible. So we can just write it down finally that the reaction is not feasible. Okay, so the key to that was writing out the half equations. If they've done that for you, great. If they haven't, write them out so that you can see clearly which direction is reduction, which is oxidation. And then you say, right, what needs to happen to this? Answer, it needs to be reduced. It can only do that if it has the more positive potential. Well, it doesn't, therefore it's not feasible. So those kind of questions are quite easy, but you do need to practice them.